This is the 9th and final part of our series on origin of the elements. At the end of the last episode, we were left with one rather large unanswered question. Where does the R process happen? We've got very good evidence that the R process happens. We can see its fingerprints in abundances. And from nuclear physics, we know what it requires. We need neutrons to be captured so rapidly that nuclei can grab onto another neutron and another before they have time to beta decay. Lots of neutrons, very fast. So we need an astrophysical environment with an extraordinary supply of neutrons available on a very short timescale. That's the requirement. But where in the universe are we going to find conditions like that? Well, perhaps we should start by asking a slightly different question. Where can we find an enormous number of neutrons? We actually encountered the answer when we talked about what happens when massive stars die. If a collapsing core doesn't form a black hole, then what's left behind is a neutron star. We're talking about something that contains roughly 1 to 2 times the mass of the sun squeezed into an object about 20 kilometers across. That's roughly the scale of a city. This picture shows New York with Manhattan here, and the sphere gives you an idea of what we're talking about. But we're putting something comparable to the mass of the sun into that volume. The density is extraordinary. A sugar cube-sized lump of neutron star material would have a mass of the order of 100 million tons. That is extraordinarily neutron-rich. Neutrons, an absolutely enormous reservoir of them. It's perfect. We need lots of neutrons, and we found them. The problem is they're all locked inside the star. For the R process, we need the neutron-rich material where nuclei can actually capture those neutrons. So now our problem is, how do we get the neutrons out? Well, remember that stars often come in binary systems. If both stars are massive enough, both can eventually undergo core collapse supernova process, and under the right circumstances, we can end up with 2 neutron stars orbiting one another. And these neutron stars don't just keep orbiting forever. As they orbit, they emit gravitational waves carrying away energy from the system, so it shrinks and they get closer and faster and closer until eventually they merge. And now something very important has changed. We've taken that neutron-rich material that was locked inside these incredibly dense objects and created an event violent enough to throw some of that material out into space. That gives us the potential environment with exactly what the R process needs. Lots of neutrons very fast. So neutron star mergers look like an excellent theoretical solution. But there's a rather important question. Do they actually make R process elements? On August 17th, 2017, something remarkable happened. Before I show you what was detected, there are 2 instruments you need to know about. LIGO detects gravitational waves, the ripples in space-time produced by accelerating massive objects. And NASA's Fermi satellite detects gamma rays, some of the highest energy light in the universe. Now watch and, most importantly, listen to what these 2 completely different instruments detected. Okay, I'm going to replay this a couple of times so that you can get it all. First, we have LIGO detecting that increase in the frequency that you hear is as they're spiraling faster and faster towards one another, and that's the gravitational wave chirp. The signal tells us that the objects are much less massive than the black holes LIGO had previously detected. Their masses are consistent with neutron stars. Let's watch that again. Spiral together, getting closer, closer, closer. Then, 1.7 seconds later, ding! Fermi detects a short burst of gamma rays. Think about what we've just done. We didn't simply make a theoretical model of 2 neutron stars merging. We detected the gravitational waves from the merger. And then, less than 2 seconds later, the Fermi detected gamma ray bursts associated with the same event. That first gravitational wave detection happened at 8:41 a.m. on that day, and 1.7 seconds later, the gamma ray burst was detected. This was known as GW 170817. That's gravitational wave on the 17th of August 2017, because we're really imaginative in how we name things. But LIGO had told astronomers that something had happened. Now we needed to find it. Where in the sky did this happen? So we have gravitational wave signal from two neutron stars merging, and just 1.7 seconds later, we get the gamma ray burst. But we have a little bit of a problem. LIGO detects gravitational waves across the whole sky. We're used to thinking about astronomy in terms of telescopes. You point a telescope at something and you know exactly what you're looking at. But neither of these detections work quite like that. LIGO doesn't point at one part of the sky. Gravitational waves pass through the Earth and the detector picks them up from essentially any direction. That makes LIGO extraordinarily good at detecting that something has happened, but determining exactly where that happened can be difficult. That's one reason having several gravitational wave detectors is so important. By combining signals from the two LIGO detectors and the Virgo in Europe, astronomers could dramatically narrow down from this blue band to this green area where in the sky the merger occurred. Fermi also detects a large area of the sky, but we can see where they overlap. To put this in perspective, we have this area here that is in dark green, that is a small fraction of the sky. The whole sky covers over 40,000 square degrees, and this is only about 28 square degrees. And that sounds pretty precise, but let's think about the size of the moon. The moon is only about 0.2 square degrees. So the area that we're looking at is still the area of 140 full moons. So it's still a big area for us to look at. We don't have the precise address of the event yet, but we know where to start looking. Now astronomers knew roughly where to look, and the alert went out to the astronomy community, and this triggered an extraordinary observing campaign. Telescopes around the world, on the ground and in space, began searching that region of sky. And now we're back to the kind of astronomy we're more familiar with. These telescopes can actually point at individual objects and determine exactly where they're looking. The game was afoot. So what were all these telescopes actually looking for? They weren't going to see two neutron stars. At a distance of 130 million light years, those are far too small to resolve. What they were looking for was something much simpler, something new. Here we have an older image from the same year, 2017, of this galaxy, NGC 4993. What we can see in this image, taken by the SWOPE telescope 11 hours after the gravitational wave detection, and we can see something that wasn't there before. See here, there is no little dot there, and here, there is a little dot there. We have a new point of light. The new point is right next to this galaxy. And once astronomers knew where to look, everybody started looking. So we have this new source, and here we can see, so this is SWOPE again, and you can see that source, but this is another telescope. This is Magellan, and you can see the same source here. And in this one, we're looking at two other detectors where it's giving you a zoom in. This is one from earlier where you see there's no little point of light there. And this is from DECAM, and you can see the point of light has appeared. And so we're starting to see it in every telescope that is big enough to see faint things. So all the telescopes saw the same new source. And now astronomers could do something much more interesting than just simply find it. They could watch and see what happens next. It changed. So here we can see, remember it was detected on the 17th of August. On the 22nd, you can see it still looks quite blobby. And then it shrinks a little and is more diffuse, and it shrinks a little more. And what we're seeing is that this source rapidly fades. So this clearly wasn't a new star that had simply appeared. This was something that was rapidly changing and fading. And remember, what we think just happened here. Two neutron stars merged. Neutron-rich material was thrown out into space, and that material was undergoing exactly the kind of nuclear reactions we've been talking about. So astronomers had a very interesting question. Could the light we're seeing actually be connected to the formation of new elements? This kind of event that we're seeing is called a kilonova. When two neutron stars merge, some of their neutron-rich material is thrown out into space. Now think back to what we've already learned about the R process. This material contains an enormous supply of neutrons, and neutron capture happens extremely rapidly. The rapid neutron capture builds extremely neutron-rich unstable nuclei, but those nuclei don't stay that way. They undergo radioactive decay as they work their way back to stability. The radioactive decay releases energy, and that energy heats the expanding material, and we see that energy escaping as light. And that glow is the kilonova. And because the radioactive material is expanding and the heating declines with time, the kilonova rapidly fades, which is exactly what astronomers watched in NGC 4993. So this is looking extremely promising. We've got a neutron-rich material, we've got radioactive decay, but can we actually show that new heavy elements were made? Here's the source again, this little spot right next to NGC 4993. Astronomers didn't just take a picture of it, they also spread its light out into a spectrum. This is a spectrum where we've got the light in different colors, in this case in angstroms, and this is high energy light. And this is how bright it is at that particular color or wavelength. The gray wiggly lines that you see here, those are the actual observations of the kilonova. We haven't really talked about spectroscopy yet, but you get the idea. Now, there's also a time sequence here. So this top curve here is 1.5 days after the detection of the kilonova. This is a day later, another day later, and another day later. So we're actually watching the spectrum evolve. At first, it's relatively smooth. There's a little bit of a dip here, but it's relatively smooth. But as we go through time, we can see more and more bumps and wiggles appearing in the spectrum. Those bumps and wiggles, or features as we like to call them, contain information about what atoms are present in the expanding material. The material is moving incredibly fast, so these aren't nice sharp spectral fingerprints. They're broadened and blended together. So astronomers calculate what the spectrum should look like with different elements present and compare those to the models. What we have here is the blue is a model that has elements up to rubidium, which is element number 37. It has 37 protons. And then the red is what you get if you use the model up to element 38, which is strontium. Now, the green is including more elements. You can see it doesn't fit well here, but the red actually is under it, so you have to follow the green lines down here. So just adding that one more element, strontium, from here, we can see that we're definitely seeing strontium forming, and we can see this dip that is appearing. So we actually have evidence of the appearance of a new element. Here is our strontium. Here is that dip in the spectrum. So basically, if there was no strontium there, it would be like the blue line. But with the strontium there, you get this dip. And so you can see the strontium is starting to form. And so what we're seeing here is that astronomers have been able to identify strontium in the ejecta of this neutron-star merger. So let's go back to the question we started with. Where does the R process happen? We need an enormous number of neutrons captured extraordinarily quickly. Neutron stars provide the neutron-rich material. A merger throws some of that material out into space. GW 170817 lets us watch it. We detected the merger, we saw the kilonova, and in its spectrum, we found freshly produced strontium. Neutron star mergers are an R process site. Are they the only R process site? Probably not. Other kinds of events may contribute, but we now know that neutron star mergers really make heavy elements through rapid neutron capture, which means we finally reached the end of our journey across the periodic table. So we finally got enough pieces to come back to the question we started with. Where did all the elements come from? And notice something immediately. A lot of these boxes have more than one color. That's because there isn't one cosmic factory for each element. Several different processes can contribute to the same element. Hydrogen and most of the helium take us all the way back to the Big Bang. Stars take those original ingredients and through nuclear fusion build progressively heavier elements. Low-mass stars manufacture carbon and other nuclei, and during their later evolution, neutron capture builds many of the elements heavier than iron. Massive stars continue fusion much further, building elements all the way up to the iron region, and their death create and disperse still more elements. And when neutron-rich environments allow neutron capture to happen extraordinarily rapidly, the R process can build some of the heaviest nuclei in nature. We now know that neutron-star mergers are one place where that happens. So there isn't one answer to the question, where do elements come from? They come from different places through different processes at different stages in the history of the universe. The hydrogen in you began with the Big Bang. Much of the carbon, oxygen, and other elements were manufactured inside stars. Dying stars created and scattered still more, and some of the heaviest nuclei were forged under conditions as extreme as colliding neutron stars. The periodic table is, in a very real sense, a history of the universe.